And so this web seminar actually is brought to you by DOE's Grid Storage Launchpad and at Pacific Northwest National Laboratory. So I'm Xiaolin Li. So I'm a material scientist at Pacific PNNL. So I will be moderating today's webinar. So let's give it maybe 1 minute or something, and then we can start. Thank you. 9:01. So we will start our webinar. So again, welcome everyone. So this is the energy storage webinar series brought to you by DOE's Grid Storage Launchpad and Pacific Northwest National Lab. So I'm Xiaolin Li from PNNL. I'm a material scientist here. So I will be moderating today's webinar. So our October topic actually is on sodium-ion battery. So I would like to let you know that we have, well, very happy to have 3 wonderful panelists with us. So they are technology experts and entrepreneurs. So they will be share with us their technologies and also their vision on the future of sodium-ion batteries. So as usual, I will first introduce the expert panel, and then we will have each panelist and to share their wonderful technology. So if you have questions during their presentation, so we appreciate if you can put these questions in the chat. So we have staff to help us collect these questions. And then later we will have a Q&A session. And so we will do our best to address all the questions there. So, I'd say I prepared, just for the panelists. So I prepared several questions to warm up the atmosphere, but I hope, with this hot topic and with all the wonderful, I'd say I appreciate, if who will be sitting here and listening will be who are really interested in the technology will take this opportunity and ask, your own questions. So this is a really precious chance. So, okay, let's get started. And so we have 3 panelists. Our first speaker actually is Dr. Ruth Sayers from Faraday Iron. So Dr. Sayers got her PhD degree from Imperial College in 2010. And she has been with Faraday Iron for almost 12 years. And she is now the director of technology. And so actually this is, my 3rd time to listen to Dr. Sayers' talk within 12 months. So every time I'm impressed. I hope you guys also will enjoy her presentation. So Ruth, if you are ready, and you can start to share your screen.
Hi, sure. Thanks, Xiaolin. Thanks for the lovely introduction. Hopefully you won't get bored. 3rd time presentation as well in 12 months.
No, yeah. Go ahead.
So I've got some slides and I'll talk through the slides, and really the topic that I was asked to speak about is to introduce Faradion. So they're very broad and an overview of the work that we've been doing at Faradion for almost the last 12 years, in fact. But the first challenge was to introduce myself. So Xiaolin gave a kind of overview of my background. I'm actually a material scientist by background, and I did do my PhD at Imperial College. I did my PhD on solid oxide fuel cells, and then as part of the kind of materials energy infrastructure in the UK, saw this opportunity for a job, what was essentially a startup at the time, and I was our 2nd employee in Sheffield at Faradion, where Sheffield is now our headquarters. So there's been a lot of growth and a lot of changes over those 12 years. But I will share my screen and I will start to talk through some of what we've been doing as part of our work here in the UK. Okay. So this went seamlessly. when we were practicing, but is now not going to go seamlessly, I think. I'm not sure why. Let me see. Okay, hopefully this works. Okay, if it doesn't work, someone will have to tell me. Okay,
It's working. It's working.
It's working. Okay, great. All right, lovely. Thank you. Okay, so really at Faradion, we focused on technology development and product development of sodium-ion batteries for energy storage solutions. So while EVs grab a lot of the headlines, our belief is that the need for energy storage that's integrated with our renewables infrastructure is significant and is meaningful in terms of the size and demand going forward. So Faradion is a UK-based company. We have 2 sites. We have Sheffield, which is kind of in the middle of the UK, and then we have Oxford, which is down in the south. And we are fundamentally a team of chemists, scientists, and engineers who do technology development and product development on sodium-ion batteries. At the end of 2021, we were acquired by Reliance New Energy, which is an Indian company which works across many different sectors. The new energy business is particularly focused on not just batteries, but also photovoltaics and the broader energy piece. At the time of the acquisition, Faradion was 16 employees. So really, we were a very small company, but we had spent the 10 years prior to that focusing on demonstrating and gathering intellectual property in the field to be able to demonstrate the value of the technology. And I thought, as this is about just giving you an overview of what we've been doing at Faradion, I wanted to kind of start with the product actually, and then work backwards to what the technology in that product looks like. And this is an example of one of our packs, our installed battery packs. So this is a Faradion designed pack that contains Faradion pouch cells. And this is installed in Australia. This particular one is in Australia, where we've got several units that are installed for residential and also commercial and industrial energy storage. And part of the challenge of taking things out and putting them out into the field is that there suddenly become a lot of unknowns that you can't always predict how performance is going to occur as a feature of those unknowns. So things, for example, such as the temperatures that you see in Australia are far more extreme to what we see in the UK, for example. So that's a different operating condition, and the kind of intensity and daylight hours and sunshine hours are also quite different in Australia to the UK. So the point here really is the value that you get from having your systems out in the field and the data that you gather from those systems when they're under operating conditions is invaluable. And that then creates a feedback loop of taking all of that valuable data that's gathered from the product and feeding that into where your next technology developments can focus. So those packs contain some of our sodium-ion pouch cells. You can see here, there's a picture here. This is in fact a 45 amp hour pouch cell. And you can see across the 2 terminals here, it's fully shorted. So this is fully discharged and it's 0 volts. And the packs in the previous slide were also fully discharged and they were actually shipped at 0 volts. So part of a unique element of sodium ion is that capability to fully discharge the cells. And that's because you can use aluminium current collectors for both your positive and negative terminals. And we have been working with the UN Committee for Hazardous Goods to be able to allocate a unique sodium ion number for transportation of sodium ion batteries, and an element of that is also to be able to take advantage of the 0 volts functionality. And I think one of the really kind of interesting and key elements of working on a technology that's at this stage and that is coming through to mass market is, right now there's a real absence of standards for sodium ion. So we're having to take the lithium ion standards and demonstrate conformance to those standards. So one of the standards that we've used for energy storage is called IEC 62619. So we have to go through the exact same tests that have been developed for that standard for lithium ion and demonstrate sodium ion against that. And I think that is an area that really needs quite a lot of emphasis as these products are now going out into the market and volumes are increasing rapidly. The activity we were doing with the UN on the transportation of these batteries actually was one of the first projects that I started working on when I came back from my first maternity leave. And to give you an idea of how long that took, my son turns 8 next week, and we're still working towards having that number formalized with the UN. So again, this element of needing to implement the standards, it also takes a huge amount of time. Here's an example of some of our 32 amp hour pouch cells, which is the size of the pouch cell that is in the energy storage system that you saw on the original slide. And these are at 160 watt hours per kilo, those pouch cells. And this is an example of some of the cycle life from those 32 amp hour pouch cells as well. Obviously, this is a key feature for energy storage because the lifetime of your pack is one of the key metrics. And you can see here we've over 3,625 cycles to 70% of the original energy, which is equivalent to 10 years of installed lifetime in a pack. And again, this is about not just considering the technology and how the technology performs, but this is also about what that means in a product and what that then looks like for the people who buy that product. So people want to buy battery packs and have them installed in their homes or their businesses, but that needs a warranty that goes alongside that. So again, it's about thinking about the commercial elements and bringing to market a technology, not just with an emphasis on the technology performance. And so very broadly, this is a real overview of what the chemistry looks like. So we use what we call a mixed phase cathode, which is basically a layered oxide that is a mixture of an O3 type and a P2 type of crystal structure. So we get a balance of high energy and also high power. We use a proprietary electrolyte, which is a sodium containing salt, typically in carbonate-based solvents. And the anode is a disordered type of carbon, a hard carbon, which has a disordered structure, which means you get much lower levels of expansion during charge and discharge when compared with graphite. I've got no idea how much time I've got left, but finally, I was just going to kind of end on what the drivers are for the technology and also the drivers for the product, because we always have technology performance as a key metric. But again, from a product development and a consumer end, clearly the cost matters, and more we see that people sustainability matters to individuals as well as they select products. So within our cathode, 4/5 of our cathode is from the 12 most abundant elements within the Earth's crust, and that abundance correlates to the price of materials as well. And there's a reference here to a paper that we published recently that looks at that a little bit more closely, as well as looking at some of the performance metrics and how those performance metrics not only mean the opportunity for sodium ion within energy storage is available, but also how within mobility there's also applications for the technology as well. And I'm just going to end by saying thank you to the whole Faradian team, which at the end of 21 was 16 people, including myself. We've now almost increased that by a factor of 4 over the past 2 years. So we've grown quite significantly, and we continue to grow. And we're always interested in hearing from people who are interested in joining the team. And I will end there.
Thank you, Ruth. You know, every time, so I learn something new, right? So I can see you reach the 160 watt-hour per kilogram. That's impressive. And also, you know, this is the first time that I learned you are the second employee of Faradian. So I think in a couple of years, I probably have to go through your bodyguards to talk to you. So, okay, thank you. So, thank you so much for the wonderful presentation. So, so I'd say I believe there probably are many questions, but we will just move on and to second speaker and third speaker. So as we mentioned, so we will collect all the questions. So again, if you have questions for Ruth, please put your questions in the chat, and we will ask during the Q&A. So let me introduce our second. Oh, so I think I'm still. I need to start my video. So let me introduce our second speaker, so Dr. Colin Wessel. And so actually Colin got his bachelor, master, and the PhD degree from Stanford. So he is the founder and the CEO of the Natron Energy. It is actually a spin out of his PhD thesis. That makes me very jealous, actually. So I was a postdoc in the chemistry department working on carbon nanotubes of graphene. Well, you know, Colin is doing these wonderful research and a big discovery. So okay, so Colin, I think the floor is yours. So you can introduce yourself. You know, I probably missed a lot of your achievements. Go ahead.
All right. Well, thank you, Xiaolin. It's a pleasure to be here. My name is Colin Wessels, founding CEO here at Natron Energy. So I've been with the company since the beginning. Started out in my garage in Palo Alto, California, and we've been scaling the business for close to 12 years now. I've done every job in the company in that time and gained a lot of perspective, not only on what it takes to build a good battery product, but also what it takes to actually bring new technologies to market. So just to double check before I get going, Xiaolin, is it correct? You can see my screen okay? Got the screen share?
Yes, I can see it.
Okay, excellent. Thank you. All right, so just quickly, a little bit of background on Natron Energy. We have a very different approach for sodium-ion batteries than the Faradian team, and I'm going to introduce that approach today. In our case, we use a different material system based on Prussian blues for our sodium-ion storage. In terms of the products the company offers, we typically sell at the system level. So that would be 48 volts and up. All of the chemistry and all the cell engineering and manufacturing we do to get to that finished product. Current headquarters are in the San Francisco Bay Area. So I'm currently in my office in Santa Clara. We are also bringing our first mass manufacturing online in Holland, Michigan. Holland is just southwest of Grand Rapids. We're at a stage now where we currently build and sell a commercial product off of our pilot line here in California. And plant bring up is in progress. We anticipate first production within the next few months, and we're going to be ramping up to a volume of over 600 megawatts per year of battery systems for industrial power customers by this time next year. Now, before I go into a little more detail on Natron's platform, I just want to briefly frame the landscape for sodium ion and talk a little bit about what Natron does and what others do, and hopefully this will provide some guidance on some of the differences between the various technologies that the three panelists are working on today. Broadly, we can segment the sodium ion landscape into two areas. The first of which is technologies that are primarily designed to replace lithium ion, and the second of which that are designed to have new performance entitlements. And that's an area that Natron works in, and we do most of our work there. And that's the technology I'm going to talk about today. In comparison, the work that Faradyne is doing, which is tremendously important, is really to address the supply chain volatility that we see in the lithium-ion space today. And the opportunity to eliminate a lot of the conflict minerals or minerals that are challenging to source. That's an opportunity that's also extremely important, for the energy storage industry and for all of us as customers. And that's something that Natron spends a little bit of time on, but that's not the main focus of what I'm going to talk about today. Rather, what I want to touch on is a chemistry that we've developed that has very unique device performance, and it allows us to use batteries in ways that lithium-ion and other incumbent technologies have not traditionally been used. And so the platform in Natron's current products is shown here. We use a material called Prussian blue to store sodium ions. And we have a first grade of Prussian blue for our anode, negative electrode, a second grade of Prussian blue for our cathode, positive electrode. Now, Prussian blue has been a commercial product for centuries. You'll find it in paints, blue jeans, all sorts of consumer products. But historically, it's only been used as a pigment. And the key innovation that we had here at Natron was we identified that the atomic structure of Prussian blue is effectively a sponge for sodium ions. And as you can see in the schematic on this slide, this atomic structure is represented by these cubic cages, and the empty spaces in the middle of each cube is just the right size for a sodium ion. So you can imagine water being absorbed into the pores of a sponge. You can squeeze the sponge, get the water back out. It's reversible, it's very fast. The same is true for Prussian blue and sodium. We can absorb and release sodium ions very, very quickly. And this is a different charge storage mechanism than you would see in conventional energy storage materials, whether that's lithium ion or lead acid or other incumbent technology classes. Now, similar to the work that Faradyne is doing, Natron also benefits from a different set of minerals. The only minerals in our cell are iron and manganese. And so we're avoiding some of the more challenging minerals that you would see in a traditional lithium-ion cell. Now, with these Prussian blue materials, we drop them into a standard device architecture. So the electrodes in the battery cell are manufactured using industry standard lithium-ion equipment. The plant that Natron's bringing online in Michigan right now was originally an automotive lithium-ion plant. And the work that we're doing is to make some subtle modifications to the existing machinery so we can drop our chemistry in. So what do we get with this platform? Well, the answer is we're getting a trade-off that results in different product performance than what we would see for lithium-ion. Now, with these Prussian blues, we get the ability to very quickly charge and discharge, so very, very high power. We also get longer cycle life than what we see in conventional battery electrodes. And we also achieve a level of safety that you just don't see with lithium. And so similar to the work that Faradyne is doing, Natron also has a very thermally stable platform. We don't have the same fire and explosion risks that you would see for lithium products. Now, the trade-off for this platform is lower voltage at the cell level and energy density, both at the cell and the system level. And for some markets, that's acceptable. For others, it's not. Natron generally focuses on industrial power markets for which energy density is not the primary decision factor for the customer. So we take this chemistry platform, we manufacture large format pouch cells, similar to what you would see for lithium ion. And then those cells are packaged into larger systems. These are modular systems that can be deployed into a variety of different operating environments. And I'll talk about markets in a moment. But typically, these would be stationary applications running anywhere from 48 volts up to a high voltage, could be 480, could be 960. And the current products are shown in the photos on the right-hand of the slide. We've got a 48-volt battery pack here, and then those packs are typically integrated into a cabinet that's about the size of a server rack. So imagine a box that's about 2 meters high, about 60 centimeters wide, and that's what you can see on the right side of the slide. Now, what we've got in the bottom left of the slide is a simple table that summarizes a handful of key device performance metrics. And the important thing to understand here is if we compare a Natron battery rack to what you would buy from a lithium-ion manufacturer, conventional NMC graphite system, what we're really making is a trade-off between the maximum power and service life of the product and the energy density. So the energy in the lithium-ion product is substantially higher than in the sodium product, but the sodium is enabling significantly higher power discharge and recharge, as well as a much longer cycle life. And that combination of high power and long cycle life can introduce some really interesting opportunities for how the energy storage is actually used by the customer. Natron is currently serving a handful of industrial power applications. A good example for us would be in data centers. It's not well known, but it actually turns out that data centers are consuming about 4% of grid power worldwide. And all of those data centers have battery backup power. So the largest stationary batteries in the world today are actually in data centers. Very few of them are fully grid interactive, but it's actually a massive energy storage install base. And this is a space that Natron does a lot of work in. We also do work in commercial scale renewables and microgrid or off-grid environments. In each of these cases, the customers are using the battery for peak shaving applications. So this would be a combination of a high power discharge and recharge, typically 5 to 15 minutes. And that battery might be cycled 10 times a day or more. And so cycle life is very important. We're also doing some work in certain types of industrial and fleet vehicles. A good example would be in a commercial aviation environment. You may need EVs to move materials around the airport. And there are certain safety risks associated with conventional lithium-ion EVs that make them very challenging for deployments into a commercial airport. So generally speaking, when we think about motive power for sodium ion, our focus areas are on types of customers that value safety and reliability in operations, as opposed to maximizing the range of the vehicle. So with that, hopefully that gives you a basic introduction to the work we're doing at Natron, and I'll turn things back over to Xiaolin.
Thank you, Colin. That's really wonderful. So I was expecting you talk about some of your UL, approve the testing, the safety side, but I think, later I'll ask that question. Yeah, safety is very important. And also, the power that Natron Energy's batteries can do is amazing. So, okay, without further ado, so let me introduce our third speaker. So Dr. Darren Tan. So we have three doctors here. So Darren got his PhD from UC San Diego, and he is an expert on solid state batteries and also recycling. So he currently is the CEO of Unigrid Battery. So I'm not quite sure whether, this technology you are going to talk about is a direct spin out of your PhD, but from, the discussion we had the other day, and also I did a little bit of homework, and I'm quite sure it's closely related. Without further ado, so Darren, so the floor is yours.
Thanks, Xiaolin, for the very nice introduction.
Thank you.
Yeah, I think as battery scientists, we always try to transfer some of our PhD training to what we can commercialize in the market, right? So I think everything is a spin-off. Let me try to share my screen. Okay, did my screen go up?
Yes, Darren, I can see it.
Great. Okay, so to briefly add on to the introduction, as Xiaolin shared, I am trained as a chemical engineer. That's where I got my PhD in. We are Unigrid is a UC San Diego spin-off company. We were founded in 2021, so we emerged from the pandemic, as some would say. We are very much a young company compared to the previous two veteran sodium-ion teams you heard from. Our mission is to bring something unique and complementary to the sodium-ion field, and we are calling ourselves an advanced sodium-ion battery company. But let me use my laser pointer. Okay. This is us in a nutshell. I think everyone in the audience here would agree that sodium is definitely the next big wave in battery technologies. We are all moving fast to seize this opportunity. Today, we set ourselves apart as the clear leader in all of North America for advanced sodium anode technologies. We've already done quite a bit of third-party validated testing for performance and safety results. Right now, we are building up our commercial traction. We very much started working on that all of this year. We're currently doing a lot of cell sampling to different partners and customers, and we've received interest for megawatt hours of cell deployment in 2024. Right now, we are working towards scaling our US domestic production and commercial deployment of sodium ion for the ESS markets. I probably don't need to spend too much time on why we need sodium. You probably heard quite a bit already from the other two speakers, but I do want to highlight two probably underlooked issues. One being that of safety that Xiaolin mentioned as well. In the last 3 months alone, there were numerous BESS fires happening all around the country in the United States, and these are mainly from lithium-ion batteries. Some of them were not for the first time either. Multiple fires occurred in the same location, one not too far from where we are at, actually, in San Diego. And we definitely need much safer chemistries if we want to prevent more of these happening. Equally important is that of supply chain. There is a need to utilize our massive domestic sodium reserves in the United States. The world has 3 orders of magnitude more abundant and cheaper sodium reserves than lithium. You know, today we put so much sodium in our food and in our bodies, it's time to put more of it in our batteries. Although sodium ion, yes, it can lower the cost, the safety, and address some of the supply chain challenges when we compare with lithium. The key missing piece that, you know, is no secret is that of energy density, specifically the volumetric energy density. A low volumetric energy density will mean that if you put sodium ion batteries in an electric vehicle, it's going to have a lower drive range. And in your ESS deployment, you're going to need double the footprint or double the number of containers for the same amount of energy. We seek to solve this problem here. And by checking all these 4 boxes, we aim to open numerous new opportunities that conventional batteries cannot address. The way we do this is through our key architecture, our technology. What we do is we take a regular sodium-ion battery and we replace the conventional hard carbon anode with a very dense tin alloy anode. This tin alloy has 3 times the capacity of carbon and about 5 times the density. So overall, your battery is a lot smaller and lighter. You can think of tin anode for sodium ion very much like the silicon anode alloy concept for lithium ion. They both have the exact same reaction mechanism. They serve very similar purposes. By how much does the energy density improve? It's easiest to look at this through a Ragon plot. Here we compare the gravimetric energy density, watt-hours per kg, against the volumetric energy density, watt-hours per liter. When we deal with electric vehicles or devices that move around a lot, we naturally care about its weight or its kilograms. And in devices that don't move at all, like in ESS application, we care about its volume or how much space it takes up. Some people call it deployment footprint. So if we look at the NMC and LFP reference point, most Chinese brand sodium-ion developers that have announced come up somewhere around here in this blue circle. And you see that this volumetric energy density and gravimetric is inferior to LFP. And this translates into additional structural and electrical components, additional thermal management, and of course, higher footprint that all adds up to your increased dollars per kilowatt hour. The customers don't want that. But if we can use a tin base anode, we can effectively double this volumetric energy density of sodium ion while retaining the cost competitiveness of sodium. To validate some of these energy density claims, one of our early work we did when we just came out was to validate this in a pouch cell. So this is one of the very first pouch cells we made. This is a 20-layer cell. It uses our proprietary tin anode versus a commercial sodium cathode that we buy off the shelf. And it's 45 grams in weight, pretty standard dimensions. And if we do the math on the energy densities, we get a specific energy of about 177 watt-hours per kg. and 460 watt-hours per liter for the entire pouch itself. So if we put this beside a commercial LFP cell, doing the same math, it shows how sodium ion cell can be competitive with LFP. When we were doing our competitive analysis, an interesting observation we made was that most of the cathode innovation teams, those you see in orange here, tend to come from Asia or originate from the EU, while most of the anode innovation teams come from North America instead. Which is why we often hear of anode innovation teams like your lithium metal teams, silicon teams, anode-free teams coming from US university spin-offs. It seems like North America is a great place for anode innovation. However, the market dynamics are starting to shift. More and more people are looking towards sodium, which is why we are all here today. And today we are one of the first to enable energy-dense sodium alloy anode innovation, but we can expect more to be adopting this in the near future. This is a summary of our team, our founding team and advisors. We are a team of highly technical founders with deep technical experience. Myself as the CEO, my teammate as Eric Wu as the CTO, we both came up from Professor Chen Chen, Professor Li Men's groups. They're well-known giants in the battery field, along with some veteran advisors that we brought on board, which is why we believe we can put forth the best performing sodium-ion battery for the target markets that we're looking at. Before I end, I just want to discuss some prospects and challenges of sodium ion, often talked about, but maybe not addressed often enough. Some of the prospects include, firstly, does sodium ion have a higher energy density than LFP? Yes, this has been proven not just by us, but many other teams out there as well. Secondly, can sodium ion really be stored at 0 volts? As Ruth showed that the data for sodium ion is tolerant to over discharge, so you can store it at 0 volts for long term, transport it, reduce a lot of your hazard risks. Third, can sodium ion really operate well at sub-zero temperatures? And this is a big yes. Below 0, you can still get more than 90% of a sodium ion cell's energy density capacity compared to maybe only a fraction in LFP. Beyond prospects, a number of challenges that sodium ion still face include its supply chain maturity, especially the sodium cathode supply chain. There's still ongoing debate about which cathodes is going to be dominant. You got your lead oxides, your polyanion, and your Persian families. So it takes some time for the industry to figure that out. When will it be cheaper than lithium ion? Today, sodium ion is roughly the same price as LFP. But we see that as the entry point, right? Sodium ion will only get better and cheaper from here. And in the long term, most expect you'll land somewhere at half the cost of LFP. Finally, is sodium ion actually safer than LFP? Well, that depends a lot on which sodium chemistry you look at. There's a broad range of chemistries out there. Some are safer, some are less safe. I know this is not actually the most satisfying answer, and the best way to figure out this, of course, to test. This is my last slide. I just want to showcase some pictures of our team and our facility, and to put word out there that we are actively shipping sodium ion cylindrical cells in 18650s to commercial partners and collaborators for testing. So if you have interest to test some of these claims yourself, check out some of its performance and safety properties, please reach out. Send us an email. We can definitely help you there and meet some of your testing needs. Hope you enjoyed this talk, and I think maybe Xiaolin can take over for, hopefully we have a good Q&A session.
Thank you, Darren, for the wonderful talk. So yeah, I think these are really great technologies. So I think this is what we planned, for different, basically different spectrum of the sodium-ion battery development, and also different stage of your companies also. So I think we already get some questions in. So the first question actually is whether you guys are okay to share your slides. I'm wondering, are you okay? Or, so some people are reaching out to ask.
The
I mean, we've
record,
already shared them. If they're on the internet, they've already been shared, essentially, no?
You know, you shared with us, so you know, so I think Shannon has these slides. But yeah, if you guys are okay, so then I think
I
I'll
think-
discuss.
Yeah, they can contact us privately if they like a copy of it. I
Good,
think we can
good to know.
probably, yeah, should be okay.
Okay, thank you, Darren. So yeah, you know, so there's some questions. So I think I'll save mine to the last. So there's one for Ruth. So you listed no fire or explosion in your list of destructive testing. So
Yep.
you know, and so with an organic electrolyte, this is a hypothesis, right? So isn't there some level of fire risk? Have you done any heat testing similar to UL 9540A?
Yep. So no, that's not a hypothesis. That's measured results. I always like to think it's quite a low bar, though, isn't it? Like no explosion. That's a. I mean, you would expect that to be the minimum requirement. So yeah, there's. I think one of the kind of fundamental things that you need to appreciate with sodium ion is that you can use carbonate-based solvents, but you can also use alternatives as well. And you're not necessarily using the exact same carbonate-based solvents that are used in lithium ion. So because you're using, in our case, because we're using a hard carbon on the negative electrode side, you can use solvents that wouldn't necessarily be compatible with graphite in a lithium ion equivalent. So there's some inherent aspects of the ability to select certain elements of the chemistry that mean that the hazards are mitigated. There's been quite a bit of thermal runaway testing that's been done, certainly in Europe, and as part of the work that we've been doing with the UN for transportation, and that showed that there was absolutely no thermal runaway in an array of sodium ion cells.
That's wonderful. Thank you so much. So I think there's also a question on safety for Colin. And so what makes your cell less flammable than lithium ion?
so that's a very good question. So, you know, similar to Faraday and natron also uses an organic electrolyte. And I think the critical thing that we need to distinguish is, you know, there's a difference between having a product that could be comprised of flammable materials, whether that's a solvent or plastic or paper or anything else, with a product that can actually generate enough heat to either auto-ignite or for whatever reason you could have a spark. And so you know, the critical issue for you know, oxide-based lithium-ion cells is that, you know, above a certain temperature, the cell itself generates more heat, all the way to the point that you can reach the auto-ignition temperature of the solvent. Hundreds and hundreds of degrees C. Now, independent of that, we could also take that electrolyte solvent out and I could go start my charcoal barbecue with it. It's like lighter fluid, completely different situation. Now, if we were to take either the electrolyte out of a Faraday cell, and I don't know exactly what it is, but you could take that, or you could take the natron electrolyte. Our electrolytes are flammable, but the cells are not. And the reason is, not only would you need to heat the cell up, you would have to heat it all the way to the auto ignition temperature of the solvents. Generally speaking, in an operating environment, if you're at 400, 500, 600 degrees C, the whole place is already burning down. So the battery is going to be the last to go. Well, we end up finding, you know, because we do all the stuff for UL 9540A and these other safety tests. What we end up finding is you heat the cell up high enough, you know, the electrolyte's going to vaporize, and there's enough vapor pressure, you're going to burst a seal in the cell. And that's true whether you use a pouch or a prismatic, any of that, they're all going to vent sooner or later. But in the absence of a spark and in the absence of a high enough temperature to auto-ignite that vapor, the vapor just dissipates. And so the consequence in the field would be, you know, we would need to ensure an adequate level of ventilation so that that vapor can dissipate. At least for natron in the industrial power markets we work in, generally speaking, that amount of airflow is already present because historically folks have been using lead acid batteries and they're worried about hydrogen venting, and that's just as bad as any solvent vapor. So I think really the critical thing here is there's a difference between a battery getting hot and having flammable materials, as opposed to having an ignition source such as a spark or an open flame next to the battery. And that's a very different situation. And generally speaking, the certifications and the tests don't look at that. They just look at whether or not the battery can start the fire.
Maybe I can add on to that too. I think Colin's absolutely right. We have done quite a bit of ARC testing, accelerated rate calorimetry testing, and we compare that against the lithium ion. And as Colin put it correctly, you know, what causes the flammability is what is the source of the spark or the heat. And almost always the case that is the NMC. At the charged state at 180 degrees Celsius, the thermal runaway occurs, and that is what causes enough heat for anything flammable to burn. Like you just take any piece of paper, this piece of paper is flammable, but what causes it to burn? That's what makes it dangerous. And most of the sodium cathodes out there can mitigate this significantly. That's what makes it a lot safer.
That's wonderful. Thanks, Darren, for chiming in. So there's a question for you also. You compared your tin alloy to the silicon alloy used in lithium ion. So is there a similar expansion issue upon charge and discharge?
Yeah, great question. It's one of the most commonly asked questions. I think it's best answered if I share one slide. We prepare this because we get this question a lot. And this,
feel free, yeah.
I think material scientists and will always appreciate this slide because it's a nice summary of how we explain this. So tin, like silicon, are both alloying materials. They both expand 300%. However, that's where their similarities end. There are fundamental differences between tin and silicon that makes tin an excellent anode in sodium-ion cell. Firstly, tin is a conductor, unlike silicon, which is a semiconductor. In silicon, you have to add a lot of carbon in it, in the anode to make it work. When carbon is a nasty source of a lot of your side reactions that you want to avoid. But in tin, we can remove all carbon additives from the electrode, so we don't have all these side reactions occurring. Secondly, silicon is very hard and it's very brittle. When it expands, you can't stop it. It's going to pulverize. It's going to break apart. That's where you lose your active materials and your capacity fades. Tin is very soft. You know, everyone held tin foils before. Just using your finger to press it's going to deform. So it remains in contact with each other, and you can keep its expansion within its own pores in the electrode level. That's why it works very well in the cylindrical cell. And finally, and I think the most important difference is their operating chemical potential. Silicon operates near lithium, which is offset from sodium, where tin is, by 0.3 volts. And near silicon is where all your electrolyte reduction occurs, and then you get all your SEI formation, all your nasty things that happen. Near sodium, there's much less SEI. That's why there's a lot of tin literature out there that show there's a very little side reaction occurring there. Of course, on the downside, you struggle a little bit more on the cathode because everything is pushed towards a high oxidative environment. I think Ruth will know this concept very well as well. Overall, this explains why tin works well in sodium, much better than silicon and lithium.
That's wonderful. Thank you, Darren. Okay, so there's one more question for Colin. So, you shared the Prussian blue electrode material, right? So the question is, do either of the Prussian blue electrodes form a solid electrolyte interface?
The answer is in our electrolyte, no. We're operating in a cell voltage such that the maximum potential of the cathode and the minimum operating potential of the anode are within the electrochemical stability window of the electrolyte. So there's no SEI. But the critical thing for the person asking this question to understand is the formation of an interface layer is really electrolyte driven. It's not a question of the particular electrode that you use. The electrode will influence the composition, but the presence of the interface layer is determined by the electrolyte.
Yeah, it's the voltage window, right? So wonderful. So there's another question for Ruth. So I think, let me find it. So yeah, thank you for the great talks. So what is the volume energy density of your 32 ampere-hour, 160 watt-hour per kilogram cell that you mentioned?
Yep, sure. So because we're using a layered oxide cathode, we can get pretty high electrode densities on that. So the kind of range of our cell volumetric energy density is 320 to 350 with that size cell.
I see. That's good. That's good. Thank you. So, while people are thinking, so let me ask my questions. So, one question is about the business model when we compare, or, the status, sodium ion and lithium ion, like a CATL or other battery manufacturers. So they don't make these materials, they buy materials, right? So for new technology, like sodium ion, for all of the technology from all of you guys, so no matter what you use, a metal oxide, or you use tin alloy, or you use Prussian blue, so the large production and of this high quality, reliable materials and the electrolyte are pretty a big challenge, right? So can you comment on this topic, like a supply chain, or what do you see future? Are you guys going to still continue this model, or like you will have some other material manufacturers to provide these materials? Yeah, this is a question for everyone, so you guys can chime in. Yeah.
Yeah, Xiaolin, I'm happy to comment on this. So I think the critical thing we need to distinguish between is the sodium ion product or any new energy storage product with new materials, is that being brought to market by an existing large battery manufacturer, or is that being brought to market by a new venture? And if I were a lithium tier one and I'm interested in maximizing my margin over time, I would need to evaluate my capabilities as a business in terms of my technology and my operations, and I'd need to look at whether or not there's a financial argument to be made that vertical integration will drive a higher margin and also a higher return on capital. And in some businesses that may be true, and in others it may not be. And furthermore, the opportune time to make a change in the model for increased vertical integration, that may come at a time when I'm choosing to roll out a new class of technology. So if I'm a big lithium OEM, that's the way I would view the world. For new venture, I would generally say it's going to be challenging. And to illustrate the point, it would just think about Natron. It would be one thing for us to take a new materials platform and just drop it into lithium ion manufacturing tools. And now we're running one plant and we can get to market and sell some product. And that alone is hard enough for a new venture to do.
Yeah.
If on top of that, we said, okay, a new business without prior experience is going to go set up a chemical plant. That's a degree of difficulty that we haven't seen a lot of ventures successfully execute on that plan. And for that reason, at least in the medium term, Natron anticipates outsourcing Prussian blue manufacturing. If for no other reason, then it would be too hard for us to do it. And that may not be the right financial decision in the very long term. We'd have to do all the analysis and understand, but in the near to medium term, there's no choice.
Good. Thank you. Ruth and Darren, do you guys want to chime in to share your thoughts?
Sure. I think from Threading's perspective, we recognized kind of when we first started that being just a materials supplier for a technology at that stage of development was not going to be sufficient, and we had to be able to demonstrate it in cells, and we had to be able to then demonstrate it in application, and so that was always part of the consideration around how we worked and who we worked with. At the same time, recognizing the point that I think Colin was kind of referring to as well, around the huge amount of capital investment that would have been required for us to go down that route of manufacturing as well. So especially you think back to only kind of 2 years ago, we were still less than 20 people. So it's taking into account all of those different kinds of considerations and the business model going forward. But I think there's certainly opportunity for it to be done differently as well with sodium and sodium ion technology in a way that it doesn't necessarily have to follow it exactly the same models that lithium ion did.
Yeah, thank you. Darren, do you want to share something?
Sure. From from Unicred's point of view, we don't make any materials. So we buy tin, commercial tin from refiners, we buy sodium cathodes from commercial sources, we buy electrolyte. We are cell technology platform developer. We sell cells, modules, and packs. We don't touch the systems. The reason is, very similar to what Colin said. We're not going to build a chemical plant as a new venture. Instead, we work with different existing chemical suppliers who are sitting on mountains of sodium raw material reserves. It's all in Wyoming, it's all in Utah, all the sodium is there. We work with them, provide the recipes, provide the opportunity for them to convert them into useful sodium battery materials. And for us, we view the cells, modules, pack as the biggest gap in the North American market for sodium. And that's why we want to focus our development on.
That's good. That's good. But actually, a follow-up question. So since you mentioned you buy all these materials, if you, I know comparing with Colin and Faraday Iron's companies, so like you guys are a little bit of early stage. Later, Colin gets a big funding of scale up, so he has this Michigan plant, right? So Faraday Iron also has been there for years. And do you see like there's in future when you need to scale it up, you worry about any reliability? And actually, this is also a question that I kind of say, this is a DOE, grid storage launchpad. In future sodium-ion battery development, do you see there's anything that you think DOE or a national lab like a PNNL can help? Or what do you see? The partnership. So to help you guys to accelerate development. So,
well, as a US company, we feel that sodium ion is the forgotten middle child of the DOE support roadmap. It's something I see Ruth laughing there because we all feel the same as well. There's been a lot of attention placed on lithium in the last 5-10 years, and right now we see signs that things are turning towards sodium. And in terms of scalability, I think sodium has a lot more potential because most of the sodium ion, as we've seen from all three companies, that can be made and produced using existing lithium ion lines. In fact, we are currently doing that as well. We rent lines that already exist, ship our materials there, produce it like you would do a lithium ion, and there's a much reduced scaling risk there. A fair bit of missing piece of the puzzle is, of course, the upstream supply chain, but there's potential for it to be entirely onshore because sodium is here. We have the ability to do it here. It's just about making the decision to focus on it and turn our attention to it, right? I hope that helps answer the question.
Yeah. Colin and Ruth, do you guys want to share anything? Is there any?
Yeah, and I'm happy to comment on this. I think what I'd say is, from the perspective of the national labs and the technology development functions of DOE, my focus would be on the material science. I think we're at a very early stage in the development of sodium ion. We're farther along. We're probably farther along than Sony was when they brought LCO to market, but it was certainly not as mature as the understanding that major lithium ion manufacturers have of either cathode chemistry or electrolyte chemistry. And there's a lot of good work to be done there. I think it's going to be significantly more challenging for technologists within DOE to support manufacturing ramp of either the materials or the batteries. And just as a simple example, it took us 2 years to go from a batch size of about 100 kilograms to batch size of a metric ton, and to get all the details we needed in composition and arrangement of point defects in the structure and particle size distribution. That was a chemical engineering problem that had to do with how you put the reactants in the tank. Yeah. And it would be very challenging for those types of material science problems to be solved in a national lab environment. And so for that reason, I would encourage DOE to really look at the materials themselves as opposed to how to scale them. There are other functions within DOE that are becoming increasingly effective in supporting not only lithium, but also sodium and other technologies to ramp up in higher volume. And just as a couple of examples, we're seeing a broader focus from DOE in the grants and loan opportunities for battery manufacturing scale up. 2 or 3 years ago, there really would have been a programmatic focus towards lithium. And I think what has changed over the years is a recognition that regardless of whether it's sodium or other technologies, there is a national strategic interest in lithium alternatives. And so I think scale up is probably going to be supported primarily by financing instruments, whereas the technology development the DOE can do really ought to be at the fundamental materials level.
Thank you, Colin. Ruth, do you want to share some final thoughts? Yeah, I understand you are from UK.
Yeah, I kind of stay outside of this slightly, which is maybe a different perspective on it as well. I think
you can talk about the support from UK, right? So
yeah. So within the UK, we have what's called the Faraday Institute, which was set up several years ago with an emphasis on UK battery business and being able to retain, fundamentally retain automotive industry within the UK, and doing that through battery research. And that's led to several designated programs, of which one of those designated programs is sodium ion. So that is the UK sodium ion players working alongside the UK academics under that programme. And I would say that is a relatively happy marriage, actually. Obviously, it brings strengths from both sides. You do, I think, need to enter into these things with an understanding about it being a joint effort and being able to play to each other's relative strengths to be able to get the best out of it.
Thank you. Yeah, sure. I know we are a little bit over the time, but I really, there's one more question that's coming in, and I feel this is, I feel an urge that I want to ask this. If you guys can stay maybe 2 or 3 more minutes. So the question is, can you talk about what do you think the sodium battery companies need from a policy and technical aspect in order to expand the growth and the market? Does anyone want to take it on? Policy, if you need any policy.
Maybe I can go first.
I'm happy to comment on this, Xiaolin. I previously discussed some of the federal support mechanisms we're starting to see for scale up, which is fantastic. I think an area where there's still more work to be done is adapting codes and standards in more efficient ways. And this is something that Ruth touched on earlier in the discussion, but it's not just about DOT. Even something as simple in the US as going through a TSCA listing process for a new material to be manufactured and sold for commercial use as opposed to development, that takes years. Yeah. And that can make things very challenging if we want to actually build products out of things that haven't been made before. And it would be a shame if we had to constrain all of our product developments to material systems that are already known and already in high volume manufacturing. So I don't know the mechanism by which those types of policy problems get solved, but I think there needs to be some kind of way to communicate between DOE and the technologists that are doing a lot of interesting product developments, and then other federal agencies that are responsible for codes and standards so that we can get those products to market.
Thank you. Darren or Ruth, do you guys want to share anything?
I see things from a top-down point of view. So yes, we definitely need more codes and standards, but we also need the entire community to work more on sodium. All the university teams, all the academic teams, national labs, we are not, there are hardly any sodium teams around. This webinar is a great start. We need more of such webinars. The research PIs, all the research teams, they need a reason to work on these topics. There are many champions of it out there, but not enough support from DOE and many other federal agencies. So, once more of these come up, there'll be a lot more innovations, there'll be new material innovations, more suppliers, more IP out there, and that's what will make the whole region competitive in sodium. And hopefully a year from now, we'll see many more companies like the 3 of us here.
yeah, hopefully, like in a year, we will be organize another webinar on sodium-ion battery, and we will see more people. Okay,
right.
thank you so much, and Darren, Ruth, and Colin, and my special thanks to Ruth. You probably have to stay out of your normal working hours. So
It's dark
yeah.
outside here. I don't know if you can see that.
Yeah. Okay. Thank you. And so that's it. Adjourn of this webinar, and hopefully I will see you guys later at future conferences.
Thank you, Xiaolin and team.
Bye bye.
Thanks for hosting us. Bye-bye.
Yeah. Thank you. Bye bye.